So in the next topic, I'm going to show you how to find the domain of vector value functions. Similar to any functions that we have been dealing with so far in mathematics, you always want to find the domain and the range of the functions. So similar to that, for the vector value function, you want to identify the domain. So the domain can be the whole real line, or subset of the real line. So why that is the case, remember you have r of t equal to x of t, y of t, and z of t, or f of t, g of t, and h of t. So the component functions are the function depend on the parameter t. So the parameter t can vary between negative infinity to positive infinity, that is the whole real line, or it's just a subset of real lines. So we're going to learn how to find the domain of the vector value function. That means you're going to learn how to define the value of t such that the vector value function makes sense. Right. So in the range, it consists of vectors. It can be two-dimensional vector or three-dimensional vectors. Because the focus on this lecture is the plane curves or space curves. If you consider two-dimensional vector value function, then you have a plane curve. Then the range of the vector value function consists of two-dimensional vectors. If you consider three-dimensional space or space curve, then the range consists of three-dimensional vector. So that means each real number, that means t value, in the domain of a vector value function is mapped to either two or a three-dimensional vector. So how would you find a domain of a vector value function? So here you have a two-dimensional vector value function. The first component is t squared, the second component is 1 over t minus 2. And then later on you ask to evaluate the vector value function at t equal to 0. But let me go ahead and evaluate this functions at t equal to 0 and see how would you possibly do that. It's very straightforward. You just basically substitute the value of t equal to 0 into the component of the vector value function and you get the results. So here you have r of 0 is equal to 0 squared, comma 1 over 0 minus 2. And this is equal to 0, comma negative 1/2. So this is a position vector with t equal to 0. So this is just a snapshot of the entire plane curve as we move through t. How would you define the domain of the vector value function? So I'm going to set up a table where you have a component on one side of the table and the corresponding domain on the right hand side of the table. So this is a 2D vector value function, so it consists of two components, t squared, which is a polynomial function of degree 2, or the power function for that matter. And the domain of that is, of course, from negative infinity to positive infinity. Similarly, you have the second component, which is 1 over t minus 2. So this is a rational function. That means you don't want the denominator to be 0. So the domain is everything excluding 2. Or in the interval forms, you can write from negative infinity to 2, union with 2 to positive infinity. Now, what is the domain of the vector value function in this case? So the domain of the vector value function is the intersection between these two domains. So if you draw the intersection between these two domains, you're going to get that the domain of r of t is going to be negative infinity to 2, union with 2 to positive infinity. So the intersection between these two domains is just this interval. Now, similarly, let's try the next example. In the next example, you have a three-dimensional vector value function or a space curve. Again, we want to find the domain of this vector value functions and then evaluate the vector value function at t equal to pi. But for now, let's just go ahead and evaluate the function at t equal to pi. So you're going to get psi of pi, comma 1 over pi minus 2, comma square root of pi minus 2. For psi of pi is going to be equal to 0, so you can simplify that a little bit. You got the first component to be 0, the second component is 1 over pi minus 2, and the last component is square root of pi minus 2. And similar to the last case, to find the domain of the vector value function, you're gonna draw a table with two columns. The column on the left consists of the component of the vector value functions, and on the right hand side is going to be their corresponding domain. So here's the tables of the component, and here's the domain. So the first component is sine of t. As you know, sine of t can run from negative infinity to positive infinity, so there's no restriction on that. And for the second component, like you see earlier, 1 over t minus 2 is a fraction or the rational functions. So the domain is everything except 2, or in the interval forms, you have negative infinity to 2, union with 2 to positive infinity. And for the last component, you have square root of t minus 2. So for the square root, the expression under the square root has to be greater than or equal to 0, or t is greater than or equal to 2, or in terms of the interval notations, you get this to be from 2 to positive infinity. And then to find the domain of the vector value function, you find the intersection of these three intervals or these three domains. And it's turned out that the domain of the vector value functions is from 2 to positive infinity and does not include the endpoint 2. So now let's move on to the next example. So in the next example, you have the functions of the form t squared minus 4, comma ln of t minus 1, comma square root of t minus 1, and you want to evaluate the vector value function at t equal to 2. So let's go ahead and do that. So here you have r of 2 is equal to 2 squared minus 4, comma ln of 2 minus 1, comma square root of 2 minus 1. Here you got the first component to be 0. The second component is ln of 1, so log of any base of 1 is 0. And the last component is square root of 1, or just 1 for that matter. Again, this is a point along a parametric curve or a snapshot in time of the vector value functions. Now, to find the domain of these functions, again, you're going to set up a table with two columns. On one side is the component of the vector value functions, and on the other side is their corresponding domain. So the first component is t squared minus 4. So this is the quadratic functions or the polynomial functions of degree 2. So the domain is from negative infinity to positive infinity. For the second component, you have ln of t minus 1. So the domain of the log function is that of t minus 1 greater than 0, or t is greater than 1 in this case. If it's written in the component form, you get this to be 1 to positive infinity. And for the last component, you have square root of t minus 1, or t minus 1 is greater than or equal to 0, or t is greater than or equal to 1. And in the interval notations, you get this to be from 1 to positive infinity. And if you find the intersection between these three domains, you're going to get that the domain of the vector value function is from 1 to positive infinity, but do not include the endpoint 1. So the domain of R of t is that of 1 to positive infinity, but do not include the endpoint 1. For the last example in this category, you have the vector value function of square root of 2 minus ti plus ln of t plus 3j plus e of tk, and you want to evaluate this vector value function at t equal to 2. You get r of 2 is equal to square root of 2 minus 2i plus ln of 2 plus 3j plus e to the 2k. So you get 0i plus ln of 5j plus e squared k, or you can write this in terms of the component form as 0 ln of 5 e squared. Similar to the last few examples, you get to make a table. On one side, you have the component of the vector value function. On the other side, the corresponding domain. So the first component, you have square root of 2 minus t. That is 2 minus t is greater than or equal to 0, or t is less than or equal to 2. In terms of the interval notation, you have this to be from negative infinity to 2, and including the endpoint 2 because of the equal sign here. Now for the second component, you have ln of t plus 3. That is t plus 3 greater than 0, or t greater than negative 3. In terms of the interval notation, you write negative 3 to positive infinity. And for the last component of the vector value function, you have e to the t. So for exponential functions, the domain is from negative infinity to positive infinity. And the domain of the vector value function, again, is the intersection of these three domains. So therefore, you can conclude that the domain of R of t is going to be from negative 3 to 2, and including the endpoint 2. Again, this is the domain of the vector value function, which is the intersection between these three domains. So now let me move on to the last topic in this lecture, where I'm going to show you how to find a vector value functions of the line passing through 2 points. And later on in an example, I'm going to show you how to parameterize a curve obtained by the intersections of the surfaces. Okay. So in example 4, I want to find a vector value function of the line passing through the points p equal to 1, 3, negative 2, and q equal to 2, negative 1, 3. So in this image, as you can see, this is a vector value functions going from one point to another point, or in this case, it's the line segment connecting the 2 points. For p is the initial point and q is the terminal point. So in lecture 9, there are 2 parts to the lecture. The first part is learn how to find the equation of the line. And in that part, you learn there are 3 different representations for an equation of the line, including parametric form or parametric equations, symmetric equation, and vector equations, where vector equations can be written as, so the vector equations of a line is r equal to r0 plus t times v, where r is the position vector that we're looking for in terms of x, y, and z. r0 is the position vector of the form x0, y0, and z0, And again, the position vector is a vector connecting the origin with the point in space. T is the parameter that we're going to specify later, and V is the direction vector. So you need the direction vector because you want to know where is the initial point, where is the terminal point. So in this case, given the information given to us, say that the initial point should be P1, 3, negative 2, and the terminal point is Q equal to 2, negative 1, and 3. So with this information, you can actually find the direction vector as follow. So you get V equal to 2 minus 1, comma, negative 1 minus 3, comma, 3 minus negative 2. This gives you 1, comma, negative 4, positive 5. So that is the direction vector. And the position vector R0, which is the starting positions, right, or the initial vector, R sub 0 is going to be 1, 3, negative 2. So in this context, again, 1, 3, negative 2 is a vector. So you put this into our vector equation formula. I get that R equal to 1, 3, negative 2, plus T is the parameter in this case, and V is the direction vector of the form 1, negative 4, and 5. Now, unlike all the situations where we explore in lecture 9, in this example, you need to specify the value of t, because this is not the line that where t is going from negative infinity to positive infinity. This is a like segment connecting the 2 points P and Q. So we need to specify the value of t such that the starting point is at 1, 3, negative 2, and the ending point is 2, negative 1, and 3. And if you notice, you can see that when t is equal to 0, you have R of 0 is going to be 1, 3, and negative 2. So this is a snapshot in time at t equal to 0. So this is the starting positions. And when t equal to 1, you have R of 1 is going to be 1, 3, negative 2, plus 1, negative 4, 5. And if you combine these two vectors together, you're going to get 2, negative 1, positive 3, which is the ending positions or at the point Q. So when you parameterize or find a vector value function of the line in space or the line segment in space connecting 2 points, the value of t usually, not always, running from 0 to 1. So here the vector value functions. The line connecting P and Q is R of t equal to 1, 3, negative 2 plus t times 1, negative 4, 5, for t is between 0 and 1. This is how you find a vector value function of the line connecting 2 points. Again, very similar to what we did in lecture 9 when you find the equation of a line through 2 points. You need the initial position vector, you need the direction vector. The difference between this example with what we did in lecture 9 is that you need to specify the value of t because you are actually finding a line segment connecting 2 points. And most of the time, the value of the parameter t running from 0 to 1 only. Okay, so now let me move on to the last example.
So in the last example, we want to parameterize the curve C obtained as the intersections of the two surfaces x squared minus y squared equal to z minus 1 and x squared plus y squared equal to 4. So our job is to express the coordinate x, y, z of a point on the curve as functions of a parameter t. So let's take a look at this picture. you have the two surfaces x squared minus y squared equal to z minus 1 given in this picture. And now the surface x squared plus y squared equal to 4 is actually a circle centered at the origins with radius 4. If you extend the circle into the surface and you blend that in with the first surface, you will have something like this, and the curve obtained by the intersection of the two surfaces give you this particular shape. And the job is to try to extract the coordinates x, y, and z of a point on the curve as a function of parameter t. So in the lecture of the polar coordinate system, you learned about the relationship in x and cosine of theta or cosine of t for that matter, and y with sine of t or sine of theta for that matter. That is, x is equal to r times cosine of t, and y is equal to r times sine of t, for r is the radius of the circle. So in this case, you have the circle x squared plus y squared equal to 4. That is the circle center at the origin with radius 2. So here you have x is equal to 2 times cosine of t, because again the radius of the circle is equal to 2, and y is equal to 2 times sine of t, and we're going to specify t in this case, which is between 0 and 2 pi. From the first equation, you can solve the z in terms of x and y. That is x squared minus y squared equal to z minus 1, and you obtain z equal to x squared minus y squared plus 1. Given that x is equal to 2 times cosine of t, you got 2 cosine of t altogether square, and y is equal to 2 times sine of t, or 2 times sine of t altogether square plus 1. Therefore, you get z equal to 4 times cosine squared of t minus 4 times sine squared of t plus 1. If you notice, 4 is a common factor between these two terms, and you get 4 times cosine squared of t minus sine squared of t plus 1. And the expressions inside the parenthesis is a Greek identity, and it gives you cosine of 2t, or this is 4 times cosine of 2t plus 1. Thus, the curve is parameterized as, so you have a vector value functions of the curve obtained by the intersection between the two surfaces as r of t equal to 2 times cosine of t, 2 times sine of t, 4 times cosine of 2t plus 1. So that's it for me for this lecture. Please let me know if you have the question. Thank you.